Classification of database management system. Classification based on data model. The most popular data model in use today is the relational data model. Well-known DBMSs like Oracle, MS SQL Server, DB2, and MySQL support this model. Other traditional models such as hierarchical data models and network data models are still used in industry, mainly on mainframe platforms. However, they are not commonly used due to their complexity. These are all referred to as traditional models because they preceded the relational model. In recent years, the newer object-oriented data models were introduced. This model is a database management system in which information is represented in the form of objects as used in object-oriented programming. Object-oriented databases are different from relational databases, which are table-oriented. Object-oriented database management systems, or OODBMS, combine database capabilities with object-oriented programming language capabilities. The object-oriented models have not caught on as expected, so are not in widespread use. Some examples of object-oriented DBMSs are O2, Object Store, and Jasmine. And now for classification based on user numbers. A DBMS can be classification based on the number of users it supports. It can be a single user database system which supports one user at a time, or a multi-user database system which supports multiple users concurrently. And then classification based on database distribution. There are four main distribution systems for database systems, and these in turn can be used to classify the DBMS. First is the centralized systems. With a centralized database system, the DBMS and the database are stored at a single site that is used by several other systems too. And then you have your distributed database system. In a distributed database system, the actual database and the DBMS software are distributed from various sites that are connected by a computer network. Third are your homogeneous distributed database systems. Homogeneous distributed database systems use the same DBMS software from multiple sites. Data exchange between these various sites can be handled easily. For example, library information systems by the same vendor, such as GIAC Computer Corporation, use the same DBMS software, which allows easy data storage between the various GIAC library sites. And fourth are your heterogeneous distributed database systems. In a heterogeneous distributed database system, different sites might use different DBMS software, but there is additional common software to support data exchange between these sites. For example, the various library database systems use the same machine-readable cataloging, or MARC, format to support library record data exchange. Now let's talk about support for fast lookup. Most database software includes indexing technology that enables sublinear time lookup to improve performance, as linear search is inefficient for large databases. Suppose a database contains n data items, and one must be retrieved based on the value of one of the fields. A simple implementation retrieves and examines each item according to the test. If there is only one matching item, this can stop when it finds that single item. But if there are multiple matches, it must test everything. This means that the number of operations in the worst case is O(n), or linear time. Since databases may contain many objects, and since lookup is a common operation, it is often desirable to improve performance. An index is any data structure that improves the performance of lookup. There are many different data structures used for this purpose. There are complex design trade-offs involving lookup performance, index size, and index update performance. Many index designs exhibit logarithmic O log n lookup performance, and in some applications, it is possible to achieve flat O1 performance. Now let's talk about policing the database constraints. Indexes are used to police database constraints such as unique, exclusion, primary key, and foreign key. An index may be declared as unique, which creates an implicit constraint on the underlying table. Database systems usually implicitly create an index on a set of columns declared primary key, and some are capable of using an already existing index to police this constraint. Many database systems require that both referencing and referenced sets of columns in a foreign key constraint are indexed, thus improving performance of inserts, updates, and deletes to the tables participating in the constraint. Some database systems support an exclusion constraint that ensures that for a newly inserted or updated record, a certain predicate holds for no other record. This can be used to implement a unique constraint with equality predicate, or more complex constraints, like ensuring that no overlapping time ranges or no intersecting geometry objects would be stored in the table. An index supporting fast searching for records satisfying the predicate is required to police such a constraint. Now let's talk about index architecture or indexing methods. First, non-clustered. The data is present in arbitrary order, but the logical ordering is specified by the index. The data rows may be spread throughout the table regardless of the value of the indexed column or expression. The non-clustered index tree contains the index keys in sorted order, with the leaf level of the index containing the pointer to the record, or page and the row number in the data page in page organized engines, row offset in file organized engines. In a non-clustered index, the physical order of the rows is not the same as the index order. The indexed columns are typically non-primary key columns used in join, where, and order by clauses. There can be more than one non-clustered index on a database table. Clustering alters the data block into a certain distinct order to match the index, resulting in the row data being stored in order. Therefore, only one clustered index can be created on a given database table. Clustered indices can greatly increase overall speed of retrieval, but usually only where the data is accessed sequentially in the same or reverse order of the clustered index, or when a range of items is selected. Since the physical records are in this sort order on disk, the next row item in the sequence is immediately before or after the last one, and so fewer data block reads are required. The primary feature of a clustered index is therefore the ordering of the physical data rows in accordance with the index blocks that point to them. Some databases separate the data and index blocks into separate files. Others put two completely different data blocks within the same physical files. When multiple databases and multiple tables are joined, it's referred to as a cluster, not to be confused with clustered index described before this. The records for the tables sharing the value of a cluster key shall be stored together in the same or nearby data blocks. This may improve the joins of these tables on the cluster key, since the matching records are stored together and less I/O is required to locate them. The cluster configuration defines the data layout in the tables that are parts of the cluster. A cluster can be keyed with a B-tree index or a hash table. The data block where the table record is stored is defined by the value of the cluster key. We know that data is stored in the form of records. Every record has a key field, which helps it to be recognized uniquely. Indexing is a data structure technique to efficiently retrieve records from the database files based on some attributes on which the indexing has been done. Indexing in database systems is similar to what we see in books. Indexing is defined based on its indexing attributes. Indexing can be of the following types. Primary index. Primary index is defined on an ordered data file. The data file is ordered on a key field. The key field is generally the primary key of the relation. Secondary index. Secondary index may be generated from a field which is a candidate key and has a unique value in every record, or a non-key with duplicate values. Clustering index. Clustering index is defined on an ordered data file. The data file is ordered on a non-key field. Ordered indexing is of two types: dense index and sparse index. In dense index, there is an index record for every search key value in the database. This makes searching faster but requires more space to store index records itself. Index records contain search key value and a pointer to the actual record on the disk. In sparse index, index records are not created for every search key. An index record here contains a search key and an actual pointer to the data on the disk. To search a record, we first proceed by index record and reach at the actual location of the data. If the data we are looking for is not where we directly reach by following the index, then the system starts sequential search until the desired data is found. Now let's talk about multi-level index. Index records comprise search key values and data pointers. Multi-level index is stored on the disk along with the actual database files. As the size of the database grows, so does the size of the indices. There is an immense need to keep the index records in the main memory so as to speed up the search operations. If single-level index is used, then a large size index cannot be kept in memory, which leads to multiple disk accesses. Multi-level index helps in breaking down the index into several smaller indices in order to make the outermost level so small that it can be saved in a single disk block, which can easily be accommodated anywhere in the main memory. A database index is a data structure that improves the speed of data retrieval operations on a database table at the cost of additional writes and storage space to maintain the index data structure. An index is a copy of selected columns of data from a table that can be searched very efficiently that also includes a low-level disk block address or direct link to the complete row of data it was copied from. Some databases extend the power of indexing by letting developers create indexes on functions or expressions. For example, an index could be created on upper, last name, which would only store the uppercase versions of the last name field in the index. Another option sometimes supported is the use of partial indices, where index entries are created only for those records that satisfy some conditional expression. A further aspect of flexibility is to permit indexing on user-defined functions, as well as expressions formed from an assortment of built-in functions. A B+ tree is a balanced binary search tree that follows a multi-level index format. The leaf nodes of a B+ tree denote actual data pointers. B+ tree ensures that all leaf nodes remain at the same height, thus balanced. Additionally, the leaf nodes are linked using a linked list. Therefore, a B+ tree can support random access as well as sequential access. As for the structure of B+ tree, every leaf node is at equal distance from the root node. A B+ tree is of the order n, where n is fixed for every B+ tree. Internal nodes. Internal non-leaf nodes contain at least n/2 pointers, except the root node. At most, an internal node can contain n pointers. Leaf nodes. leaf nodes contain at least n over 2 record pointers and n over 2 key values. At most, a leaf node can contain n record pointers and n key values. Every leaf node contains one block pointer p to point to next leaf node and forms a linked list. B plus tree insertion. B plus trees are filled from bottom, and each entry is done at the leaf node. If a leaf node overflows, split node into two parts. Partition at I equals n plus 1 over 2. First I entries are stored in one node. Rest of the entries, I plus 1 onwards, are moved to a new node. Ith key is duplicated at the parent of the leaf. If a leaf node overflows, split node into two parts. Partition the node at I equals n plus 1 over 2. Entries up to I are kept in one node. Rest of the entries are moved to a new node. B plus tree deletion. B plus tree entries are deleted at the leaf nodes. The target entry is searched and deleted. If it is an internal node, delete and replace with the entry from the left position. After deletion, underflow is tested. If underflow occurs, distribute the entries from the nodes left to it. If distribution is not possible from left, then distribute from the nodes right to it. If distribution is not possible from left or from right, then merge the node with left and right to it. Indexed file organization. An indexed file contains records ordered by a record key. A record key uniquely identifies a record and determines the sequence in which it is accessed with respect to other records. As we have seen already, database consists of tables, views, index, procedures, functions, etc. The tables and views are logical form of viewing the data, but the actual data are stored in the physical memory. Database is a very huge storage mechanism, and it will have lots of data, and hence it will be in physical storage devices. In the physical memory devices, these data cannot be stored as it is. They are converted to binary format. Each memory devices will have many data blocks, each of which will be capable of storing certain amount of data. The data in these blocks will be mapped to store the data in the memory. Any user who wants to view these data or modify these data simply fires SQL query and gets the result on the screen. But any of these queries should give results as fast as possible. But how are these data fetched from the physical memory? Do you think simply storing the data in memory devices give us the better results when we fire queries? Certainly not. How is it stored in the memory, accessing method, query type, etc. makes great effect on getting the results. Hence, organizing the data in the database, and hence in the memory, is one of the important topics to think about. Let's talk about the types of file organization. In a database, we have lots of data. Each data is grouped into related groups called tables. Each table will have lots of related records. Any user will see these records in the form of tables in the screen. But these records are stored as files in the memory. Usually, one file will contain all the records of a table. As we saw above, in order to access the contents of the files, records in the physical memory, it is not that easy. They are not stored as tables there, and our SQL queries will not work. We need some accessing methods. To access these files, we need to store them in a certain order so that it will be easy to fetch the records. It is the same as indexes in the books or catalogs in the library, which helps us to find required topics or books respectively. Storing the files in certain order is called file organization. The main objective of file organization is optimal selection of records, that is, records should be accessed as fast as possible. Any insert, update, or delete transaction on records should be easy, quick, and should not harm any other records. No duplicate records should be induced as a result of insert, update, or delete. Records should be stored efficiently so that cost of storage is minimal. There are various methods of file organization. These methods may be efficient for certain types of access or selection, meanwhile it will turn inefficient for other selections. Hence, it is up to the programmer to decide the best suited file organization method depending on his requirements. Some of the file organizations are sequential file organization, heap file organization, hash or direct file organization, indexed sequential access method, B+tree file organization, cluster file organization. A B+tree is an n-ary tree with a variable but often large number of children per node. A B+tree consists of a root, internal nodes, and leaves. The root may be either a leaf or a node with 2 or more children. A B+tree can be viewed as a B-tree in which each node contains only keys, not key value pairs, and to which an additional level is added at the bottom with linked leaves. The primary value of a B+tree is in storing data for efficient retrieval in a block-oriented storage context, in particular, file systems. This is primarily because, unlike binary search trees, B+trees have very high fan-out, or number of pointers to child nodes in a node, typically on the order of 100 or more, which reduces the number of I/O operations required to find an element in the tree. The riser FS, NSS, XFS, JFS, REFS, and BFS file systems all use this type of tree for metadata indexing. BFS also uses B+trees for storing directories. NTFS uses B+trees for directory and security-related metadata indexing. ext4 uses extent trees, a modified B+tree data structure, for file extent indexing. Relational database management systems such as IBM DB2, Informix, Microsoft SQL Server, Oracle 8, Sybase ASC, and SQLite support this type of tree for table indices. Key-value database management systems such as CouchDB and Tokyo Cabinet support this type of tree for data access. Indexes are a common way to enhance database performance. An index allows the database server to find and retrieve specific rows much faster than it could do without an index. But indexes also add overhead to the database system as a whole, so they should be used sensibly. PostgreSQL provides several index types: B-tree, hash, gist, spgist, GIN, and BRIN. Each index type uses a different algorithm that is best suited to different types of queries. By default, the createIndex command creates B-tree indexes, which fit the most common situations. B-trees can handle equality and range queries on data that can be sorted into some ordering. In particular, the PostgreSQL Query Planner will consider using a B-tree index whenever an indexed column is involved in a comparison using one of these operators: less than equals to, equals, greater than or equals to, greater than. Constructs equivalent to combinations of these operators, such as between and in, can also be implemented with a B-tree index search. Also, an is null or is not null condition on an index column can be used with a B-tree index. The optimizer can also use a B-tree index for queries involving the pattern matching operators like and tilde. If the pattern is a constant and is anchored to the beginning of the string, for example, call like foo%, or call tilde foo, but not call like %bar. However, if your database does not use the C locale, you will need to create the index with a special operator class to support indexing of pattern matching queries. See section 11.9. It is also possible to use B-tree indexes for I like and tilde asterisk, but only if the pattern starts with non-alphabetic characters, that is, characters that are not affected by upper or lowercase conversion. B-tree indexes can also be used to retrieve data in sorted order. This is not always faster than a simple scan and sort, but it is often helpful. Hash indexes can only handle simple equality comparisons. The query planner will consider using a hash index whenever an indexed column is involved in a comparison using the equal sign operator. The following command is used to create a hash index. Gist indexes are not a single kind of index, but rather an infrastructure within which many different indexing strategies can be implemented. Accordingly, the particular operators with which a gist index can be used vary depending on the indexing strategy or the operator class. As an example, the standard distribution of PostgreSQL includes gist operator classes for several two-dimensional geometric data types, which support indexed queries using these operators. Indexes are special lookup tables that the database search engine can use to speed up data retrieval. Simply put, an index is a pointer to data in a table. An index in a database is very similar to an index in the back of a book. For example, if you want to reference all pages in a book that discusses a certain topic, you have to first refer to the index, which lists all topics alphabetically and then refer to one or more specific page numbers. An index helps to speed up select queries and where clauses. However, it slows down data input with update and insert statements. Indexes can be created or dropped with no effect on the data. Creating an index involves the createIndex statement, which allows you to name the index, to specify the table, and which column or columns to index, and to indicate whether the index is in ascending or descending order. Indexes can also be unique, similar to the unique constraint, in that the index prevents duplicate entries in the column or combination of columns on which there's an index. PostgreSQL provides several index types: B-tree, hash, gist, spgist, and GIN. Each index type uses a different algorithm that is best suited to different types of queries. By default, the createIndex command creates B-tree indexes, which fit the most common situations. A single column index is one that is created based on only one table column. A multi-column index is defined on more than one column of a table. The basic syntax is as follows: createIndex index-name. On table-name, column 1, column 2 name. Whether to create a single column index or a multi-column index, take into consideration the columns that you may use very frequently in a query's where clause as filter conditions. Should there be only one column used, a single column index should be the choice. Should there be two or more columns that are frequently used in the where clause as filters, the multi-column index would be the best choice. Unique indexes are used not only for performance, but also for data integrity. A unique index does not allow any duplicate values to be inserted into the table. The basic syntax is as follows: create unique index index-name on table-name column name. A partial index is an index built over a subset of a table. The subset is defined by a conditional expression called the predicate of the partial index. The index contains entries only for those table rows that satisfy the predicate. The basic syntax is as follows. Create index index-name on table-name conditional expression. Implicit indexes are indexes that are automatically created by the database server when an object is created. Indexes are automatically created for primary key constraints and unique constraints. Example: the following is an example where we will create an index on company table for salary column. Hash create index salary-index on company salary. Now let us list down all the indices available on company table using /d company command. #/d company. This will produce the following result, where company key is an implicit index, which got created when the table was created. Query Optimizer uses heuristic algorithms to evaluate relational algebra expressions. This involves estimating the cost of a relational algebra expression, transforming one relational algebra expression to an equivalent one, choosing access paths for evaluating the sub-expressions. Query optimizers do not optimize, just try to find reasonably good evaluation strategies. Query evaluation problem. An SQL query is declarative, does not specify a query execution plan. A relational algebra expression is procedural. There is an associated query execution plan. Solution: convert SQL query to an equivalent relational algebra and evaluate it using the associated query execution plan. Equivalence preserving transformations. To transform a relational expression into another equivalent expression, we need transformation rules that preserve equivalence. Each transformation rule is provably correct, that is, does preserve equivalence, has a heuristic associated with it. Selection and projection rules break complex selection into simpler ones. Cond1, Cond2, R, Cond1, Cond2, R. Break projection into stages. ATTR, R, ATTR, ATTR, R. If ATTR, ATTR commute projection and selection. ATTR, Cond R, Cond ATTR, if ATTR all attributes in Cond. Commutativity and associativity of join, and Cartesian product as special case. Join commutativity, RSSR, used to reduce cost of nested loop evaluation strategies. Smaller relations should be in outer loop. Join associativity, RST, used to reduce the size of intermediate relations in computation of multi-relational join first compute. The join that yields smaller intermediate result, n-way join, has Tn n exclamation point. Different evaluation plans. Tn is the number of parenthesized expressions. N exclamation point is the number of permutations. Query optimizer cannot look at all plans. Might take longer to find an optimal plan than to compute query brute force. Hence, it does not necessarily produce optimal plan 9. Pushing selections and projections. Cond R, S, R. Cond S, Cond, relates attributes of both R and S. Reduces size of intermediate relations since rows can be discarded sooner. Cond RS, Cond RS. Cond involves only the attributes of R. Reduces size of intermediate relations since rows of R are discarded sooner. ATTRS, ATTR, ATTRRS. If attributes R, ATTR, ATTR, attributes R, reduces the size of an operand of product 10. Equivalence. Example, C1, C2, C3, RS. C1, C2, C3, RS. C1, C2, R, C3, S, C2, R, C1, C3, S, assuming C2 involves only attributes of R, C3 involves only attributes of S, and C1 relates attributes of R and S.